So hello everyone, and welcome to week 4 on Weld 40 at Mount San Antonio College. And this lecture I wanted to talk to you about oxyacetylene regulators and also oxyacetylene hoses and how they're put together. I don't know if you're going to remember all of it, but if you pick up just bits and pieces, it just seems to all kind of eventually blend itself for you to get an overall picture so that you operate safely. Whether you hear it here during this lecture or you read it in a book, doing it a few times, taking a couple classes, the information starts to really be put together and you start being able to operate in a safe way. And that's what this is all about. So if you just get those bits and pieces, hopefully it's the more important items, it will help you as a welder and to work safely in the welding industry, whether it be at a fabrication shop or in the field itself. But let me start with the regulators. So these are the samples of the regulators themselves. Let me get a better picture of it. Like here. So this one here is an acetylene regulator, and notice the red marks here above the 15 psi on the acetylene regulator. As we talked about earlier, that acetylene becomes unstable above 15 psi. It's a hydrocarbon. So we don't want that to occur, whether it's in an acetylene cylinder that I tried to talk about earlier, that the acetylene cylinder uses the calcium silicate filler. It also uses the acetone that absorbs 24 to 35 times its own volume. And that acetone, as it increases atmospheric pressures, which I was trying to describe if you're into diving in the ocean, at 33 feet, you're at 14.6, 14.7 psi. So for each atmosphere, the acetone actually works better. So as the pressure rises in the acetylene cylinder, it absorbs the gas even better. So it's the acetone and the calcium silicate in the cylinder that helps stabilize the gas. Then upon usage, we don't want to go above 15 psi. So I'll show you one more time. You'll notice on that cylinder that above the 15 psi mark, it actually has red zone there, which means at no time should that needle on that gauge go above 15 psi. And that's the reason for it. On the oxygen regulator, that one, of course, on the high end is going to read higher than 2200 psi. If you take a look at it, it's maxed out, this one at 4000 psi on the high end, and then on the usage side, it goes up to 200 psi. You take a look at that. And then this is the pressure regulating screw. You'll have this on both of the regulators right here. It's a movable part. This pressure regulating screw, if you actually unscrewed it all the way, you're not going to harm anything. It just comes apart. It's just when you go to put it back in, some of these have nylon threads. So you want to be careful about cross-threading these when you're putting the pressure regulating screw in. So what I do is I like to go backwards on it just so it kind of catches the thread. And then just lightly make sure it's in the right groove and you can put it back into place. Now, as I move this forward on this pressure regulating screw, it's going to catch a spring right there. I can feel it in the pressure regulating screw. Right there, I sense that right at the spring. So I'm starting to push on the spring right there, and I'm starting to open up this valve. It's a nozzle, actually, within the regulator itself, and I'm starting to open the regulator by moving the pressure regulating screw and moving the spring itself. So we're going to talk about that in just a moment, but that's the basic concept of this. To remove the pressure from the spring, I back to the left And it's very easy to move at that point because there's no load, if you will, onto the spring itself. So let's talk about the regulators and just kind of a background on them. On the regulators, the oxygen pressures, as we talked about, reaches 2200 psi at 70 degrees Fahrenheit. And the acetylene cylinder, we're at 250 psi when you get those cylinders filled. Keep in mind that even the 2200 psi or the 250, we have to have a mechanism to be able to take that pressure and reduce it to where it's a working pressure. And we want to be able to use that pressure while it's not fluctuating. In other words, I should be able to take 2200 psi and reduce it down to 5 psi, which is what we're using right now with the oxyacetylene welding, 5 psi. And while I'm using that 5 psi, it shouldn't fluctuate. In other words, it shouldn't go 5.5, 4.5, because what would happen on your flame is it would expand and then it would contract, and it would really affect your movement and usage of the torch while you're doing the welding. So that 5 psi, it has to be consistent. And that's the purpose of these regulators. Very, very important that I can take the pressure within a cylinder at 2200 psi and bring it down to 5 psi. So we'll start talking about the types. There's two types. There's a 1 stage and there's a 2 stage. The 1 stage is for a manifold system. That's where you have a bulk of cylinders where they're stored, and you've already have a heavy duty regulator there. Those go in through a piping system, connect to the regulator, and the pressure is reduced at that heavy duty regulator, and then it's piped in through the piping system. Now that's called a manifold system. That's what we have here at Mount San Antonio College. And it's used because it's very efficient in a learning atmosphere. On the last talk, I talked to you about that. That's what we used on the Navy ship. They had a manifold system there where they had a setup of piping and they ran hoses throughout the ship. And we used that in order to draw off that in order to get our oxyacetylene. So usage of a manifold system is not uncommon. This happens to be a manifold regulator. You can see it just has 1 gauge on it right here. Again, it's an acetylene, so you can see at the 15 psi mark, it goes into the red zone, and it's got the pressure regulating screw. Different type, but same movement, where you back it off, and right there I can kind of sense the spring tension right there. So I'm going to back it away and keep the regulator closed. Okay, so the other type, other than the 1 gauge and the manifold, is the 2 stage, and that is the normal regulator that you would use on oxyacetylene cylinders, just as I showed earlier, right here. And you can see that each of these have 2 gauges on them. So I'd like to take just a moment and explain that to you. Within the regulator itself, of the 2-stage regulator, it's got 2 compartments. And the first compartment is called the upper stage of the regulator, or the high pressure stage. But just to keep it easy conversational, we're going to call it the upper stage. And within that, it's got a spring right here, marked as a spring. It's got a flexible diaphragm moving right here, and connecting to that is a nozzle. And it's a nozzle. And that nozzle is preset from the manufacturer. So what I'm trying to tell you is that in the upper stage, your pressure on the oxygen comes in at 2200 psi. It goes in, and it comes out of that upper stage at 200 psi. Also, that upper stage, it has a gauge on it. It's one of these. So I can take a look. This is the upper stage, this regulator, and this this gauge is telling me how much pressure is in the cylinder. Obviously, as I start using the 2200 psi, it's going to start going down, and I can tell by looking at this gauge whether or not there's oxygen in the cylinder. It might be 500 psi or 1000 psi, but it's going to give me a running count by this gauge that's connected to the upper stage. Now, this upper stage, it's preset by the manufacturers in the industry to where it releases 200 psi out of this upper stage. Once it leaves the upper stage, then it goes into the lower stage. And in the lower stage, again, it feeds in at that same 200 psi. But in this stage, the pressure regulating screw is what regulates how much pressure is actually being discharged to the hose and to the torch. So here I'm writing 0 to 200 psi because it depends on the activation of this pressure regulating screw. Of course, the more that you press onto this spring, the more that it opens and you'll be able to draw the pressure. But the most you're going to get out of this is 200 psi. That's all these regulators will feed you for the oxygen. In addition to that, this stage also has a gauge. So that gauge is going to tell me what I'm actually drawing at the torch itself. So I'd like to take this one more time to you, and I want to show you that this upper stage right here reads to 4,000 psi. That's in case, we talked about that it has 2,200 psi in it. But if you're in a hot area, if you're in a desert somewhere where you have hot temperatures, the gas will expand. So the gauge allows that for that expansion and gives you a current reading on whatever gas you have, what it's reading for the cylinder. This is the upper stage. And then this one right here is connected to the lower stage, which of course is being operated by this pressure regulating screw. And this one, if you can look here, reads all the way up to 200 psi. And the reason why is because that's all you're going to get out of this upper stage is 200 psi. On the acetylene regulator, that one on the upper stage reads to 400 psi. And then on the lower stage, you can see that it reads, obviously, whatever's set here on the pressure regulating screw. But that one goes to 15 psi. And you see once it reaches the 15 psi that it clearly tells you that it's a problem. You know, that you're into the red zone. So this needle should never be into the red zone when you're using the acetylene gas. Lastly, what I want to say, I want to go back and talk to you about this one stage. In a manifold system, I don't know if I even have an empty space here, but if I have a storage of oxygen cylinders, and all these oxygen cylinders all feed a heavy-duty regulator, and then it goes through a series of piping over here to where a welder is standing, doing work. This high-pressure, heavy-duty regulator, it's already reduced the pressure within these cylinders. It's already reduced it from 2,200 psi, and here at the college we set this at 80 psi. But my point being is that it's already been reduced, so I don't need to have a two-stage in a manifold system. I only need one stage. And guess what? These are cheaper than the two-stage. They're at least half the cost. So it's much cheaper and no reason not to use these manifold one-stage regulators. And if we take a look at the manifold regulator, one stage, again, you'll just see the lower stage. That's it. And it goes up to the 15 psi and then into the red zone for the acetylene. So that is a demonstration of the regulators. Oh. Um, it's important for you to know that the pressures while you're using these regulators, it can't fluctuate. So it's amazing to me that they're that rugged. And of course, this stage is much more rugged than the lower stage. This is the one that's taken the bulk of the pressure and reducing it to 200 psi. This I'm going to say less rugged, and it's certainly the more sensitive of the two. At this time, I just want to mention to you, when you're opening a valve on an oxygen or an acetylene cylinder, just crack the valve. Just barely crack it when you go to open it, every time. Just crack it. Allow the gas to go in to the regulator and let it seat. And once it's seated, then you can open it up. Obviously on the oxygen, we're going to open it up all the way. On the acetylene, we're only going to open it 1.5 turns. But whenever I go to open these to begin with, I just barely crack them. And then let the gas go in, so that I'm not walking up and just opening up a valve and letting the gas just fly into the regulator and then letting it fly into the less rugged of the two sections of the regulator and possibly doing damage to this flexible I've got a flexible diaphragm here. So there is there's a reason for it. We want these regulators to last a while. You invest something, these things, you could spend $500 on one of these regulators, and it should last you your lifetime, literally. In the welding industry, it should last you 35, 40 years if you take care of it. When I was working as a welder, we always took the regulators in once a year, and we got them calibrated. You can take them into a weld supply place and send them off, and they'll get them calibrated for you. I don't want to mention the names of the companies, but they're there. And for the welding stores, we'll let you know. They'll bring them, they'll get them calibrated and give them back to you. If the needles are getting stuck, get it calibrated. Go and get it fixed. If it's not reading properly, something gets stuck. It's not uncommon. We had other types here. This particular type, you can't back out. But we used to have ones that could back out, and people would try to re-screw them back in, and with the nylon threads, they would cross-thread them. And so we'd end up with a bunch of cross-threaded pressure regulating screws, and we'd have to send them out and get a re-nylon thread. So we've gone to a different type that when you back it away, it stops on its own. So there's no cross-threading. But we do the best that we can, and no one would do that on purpose. I'm just saying that when you go if they do back out on the pressure regulating screw, just be careful, as you're trying to reset it so that it doesn't get cross-threaded and reset. So we don't want to open the cylinder valves suddenly. We want to loosen the pressure regulating screw. So before I'm going to open up a cylinder, right, I want to make sure that this pressure regulating screw is backed away to where it's free, like this. I can move it freely. That way I know there's no load on this spring right here, and the regulator is closed. It's closed. If this is screwed in and it's pushing on the spring, that means that the regulator is open, and I don't want to open the valve at that time. I want the regulator closed, and then I'll crack the valve. After it cracks, then on the oxygen, I'll open it all the way. On the acetylene, I would open it 1.5 turns. Lastly, I want to tell you, this is in the early 1980s. They started putting check valves. This is actually a check valve right here on the end of the regulator. They started putting these on there so that the gases, anything from where the welder's working, can't travel back to and into the regulator or into the cylinder itself. And so these started going on. We use them on the acetylene, and we also use them on the oxygen. If you're welding and temperature drops in the hose, there is a potential for that fire traveling through the hose and back to the cylinder. Couple things on that. My last lecture, I talked to you that acetylene cylinder is actually designed to absorb that flame coming back. For one, that's one of the tests that they do on the cylinder itself. But also we have these check valves so that if the pressure drops, the check valve closes so that the flame couldn't reach beyond this point. And we started putting these check valves on these regulators in the early 1980s or so. If a gauge creeps, if the needle creeps while you're using it, or moves, while you're using it, get it repaired, get it fixed, go and get it calibrated. We don't use any oil, we don't use any grease on any of this. The oxygen regulators have right-handed threads. The acetylene regulators have left-handed threads. So while I'm talking about that, most people know what right-handed threads are. They're the normal threads in the industry. But on the acetylene, you're going to notice the groove right here on the nut itself that's used to turn. And it's got the groove there telling you that it's a left-handed thread. So when I go to connect this to an acetylene cylinder, I have to move to the left in order to tighten it. It's direct opposite of the oxygen. And that's because they don't want any possible mismatch between the oxygen and the acetylene. They're two completely separate usage items. And by the way, that's everything. That's all the hose connections completely from to the cylinder, to the hose, and then all the way for the connections to the torch itself. Everything on the oxygen is right-handed, everything on the acetylene is left-handed, noted by that notch in the fitting telling you that it's left-handed. And I think that kind of covers about this. I should say, I have to say my last comment again, but in the manifold system here at the college, where we're feeding it into a piping system, we have an additional safety mechanism in place. It's called a hydraulic back pressure valve. And this hydraulic back pressure valve, what it does is the supply of oxygen cylinders here, it is fed into a water tank that's filled with water. The gas goes in and bubbles out of the water, and then it goes into the collection pipe where the welder uses it. So if I had something to mark with, so the welder would be over here, if you will, and the oxygen cylinders would be here, that would be fed into this hydraulic back pressure valve. And here in the welding department, we have several of these. There's 3 on the wall, 1 on this side, 2 over here. We also have them outside where the cylinders are being stored. We have hydraulic back pressure valves there also, so that there's no chance that any flame could potentially feed back into the system. Again, it's just more and more safety that's installed into the manifold system technology to keep it safe for usability. Okay, so that kind of finishes my lecture on the regulators, and I'd like to talk to you about hoses. The oxyacetylene hoses. The oxyacetylene hoses are manufactured by the Compressed Gas Association, the CGA, and the Rubber Manufacturers Association rules. That means you just can't go out and make oxyacetylene hoses. You have to follow their rules when you're manufacturing the hose. I will do my best to show you some of the markings on this hose. You can see a Gemini, 1/4 inch, grade R, acetylene right there, 200 PSI, and the markings there, Rubber Manufacturers Association, and this happens to be a Goodyear type manufacturer of the oxyacetylene hose. It's measured by inside diameter, and the handout, it's part of the handout on Canvas for you. You can see that there's several manufacturers of torches and fittings in the industry. And here at the college, we use Victor. So what we're trying to say here is that a Victor aught tip is equal to a Craftsman 1. Or if you're using Marquette, a 2B. If you're using an Weld, a number 4. That is the equivalent. A lot of our welding here, we're using an aught tip. And so all this does is just a reference sheet to allow you to use other different types of manufacturers if you choose to, and see the compatibility with that using the Victor as the base. We do use Victor here, and you know, some of these tips and torches we've literally had for 35 years, 40 years here at the college. We've used them that many years. So it's a well-made product, but that doesn't mean you can't use the other styles. But leading into this part of the lecture, back in the days, there were different manufacturers. And so they would have a Marquette hose and a Victor regulator. And of course, they didn't have the proper adapters. And what was happening is that they were forcing things together. And there was a time during this time where there were fires and there were accidents. And it kept happening until January 1st, 1926. In January 1st, 1926, they set the regulations that for any connections for the hoses, it's 3/8 outside diameter, 24 threads per inch for the hoses. For the regulators, 9/16 outside diameter, 18 threads per inch, and that is throughout the industry. That means who's ever making the hoses or the regulators, it's all going to interconnect with each other to eliminate any of these leaks and potential fires. The other thing to talk to you about is the grade of hoses. There's 3 grades, T, R, M, and R. And one really important item to know about this. A grade T hose is flame and oil resistant. A grade RM hose is oil resistant, cover. And a grade R hose is neither the cover nor the liner of the hose itself is oil resistant. So again, I'm going to try to move close here so that you can see the hose and what it looks like. The outside part of the hose is vulcanized rubber. Let's see if I can. The inside of the hose is a gum rubber. It's the black rubber. And between the gum rubber and the vulcanized rubber is braided rayon. It's white color. I don't know if you can see it. You barely see the ends of the rayon, the braided rayon between the 2 layers right there. And that's what gives it its pressure rating of 200 PSI. So up here, I did my best to try to draw it for you. That's kind of what it looks like. You have vulcanized rubber on the outside. You have gum rubber on the inside, this area right here. I'll try to cross hatch that so you can kind of see it. That's the gum rubber. And then between the gum rubber and the vulcanized rubber, you have that white braided rayon that gives the hose its strength and the 200 psi. So these hoses are rated at 200 psi. The hoses are measured every 25 feet. So you've got markings on the hose. They're required to do that. We talked about it being measured by the inside diameter. Very normally, we would use 1/4 inch hose. When I was working in the industry, I had my own 10-foot 3/16 whip. So I had my own 10-foot 3/16 oxyacetylene hose, and I would connect that to the 1/4 inch hose and then use that with my torch. It would just be a little bit lighter as I'm doing all my welding and cutting for the day. So that's not uncommon in the industry either to have that. The outside of the hose, I'll try to get a demonstration for you. This type of hose is called a VD hose, where it's got a rubber webbing, if you will, to hold it together. It's called VD. You can also buy the single hose, just like this. And there's another style where, they're separated hoses. They're single hoses, but they just use like a brass connector like that to hold the hoses together. Most of the time in the industry, I see the rubber web, this style hose being used, just for its ease of use. So the important thing on the grades of hoses that I wanted to talk to you about is that the acetylene gas, acetylene gas can be used for all three of these grades of hoses, T, R, M, or R. But if you're using a hydrocarbon, if you're using a gas other than acetylene, you must use grade T because the other types of gases disintegrate the gum rubber. And so here I wrote, any gas other than acetylene, you're required to use a grade T. So if you want to use the Apache gas, you want to use the MAP gas, all of that has to be the grade T hose, which of course, it's the most expensive to buy. Using the acetylene gas, if you look at some of the flame and oil resistant cover, so that means if you're around oil a lot on the floor, maybe it's being dragged through oil, that might be an option. And then here, neither the cover nor the liner is oil resistant. And I'm here to tell you that everywhere in the industry, whether it's a fabrication shop, whether it's out in the field, everybody uses grade R. That's what they use. That's what they buy. That's what they purchase. That's what's everywhere. But keep in mind, if you're not using acetylene gas, you have to have grade T for whatever type of gas for the flammable side that you're going to be using. The fittings. If I have a demonstration of that, I'll try to get a couple of the fittings. So here's a left-handed hose connection. You can see the notch in it telling you that it's a left-handed thread. Here's an oxygen nut that would be just a normal right-handed thread to use. Here we go. Normal right-handed thread. And I tried to get in the acetylene one. I think I just kind of showed you. So I already showed you for the acetylene, it's got the left-handed. Here's a connector, a hose connector. And that's a hose connector. This is for oxygen. It would be an oxygen hose here and an oxygen hose here. You would just connect them. If you were connecting like 100-foot hoses together, you would use this particular coupling. And then if this was an acetylene connector, it would have a notch right here, just like that, telling you that that would go with the acetylene hose. And this is a close-up picture of a ferrule that I want to demonstrate to you right now. So if there's a leak in the oxyacetylene hoses, we don't want to put tape over the hose. I actually had this happen. I was working on a late night shift. I came in, somebody had put tape over the hose, and while I was welding, the acetylene obviously was leaking because it was just duct tape, and it caught on fire. So I had to go and shut the acetylene gas off. And my point being is that if you ever see a leak in an oxygen or an acetylene hose, walk right up and cut it. Just cut it right in half. Because if they cut it, then they have to repair it. And that's what I wanted to demonstrate to you. One of the handouts for this lecture is it shows you the hose, it shows you a ferrule, it shows you a nut, shows you a nipple, splice connector, and also the hose coupling itself. And this is actually a connection using the nipple connection, where it would be a hose, a ferrule, the nut, and the nipple. That is used for the connection for the hose. And if there's a hose splice where you've cut the hose, we would use a splice connector using a ferrule on each side, putting the hoses back together. And that's what I wanted to show you right now, where if these hoses were apart from one another, that I would put a ferrule. You have to get the right size ferrule for the size hose that you have. And then you would get the splice connector, and the splice connector goes into the gum rubber, connects in on that, and then the other end of the splice connector goes into the other end of the hose. Just like that, where you have that kind of connection. It's not uncommon for people to use soap to get these connectors together. But once they're connected, you would get, these are sold in a welding store, and they're used to crimp the ferrule. Just like that, you crimp it once, you turn it 90 degrees, and you crimp it again. So I'll try to do it from the side. On this side, you crimp it once, like that, and release. I'll do my best to try to do it up in the air so you can see it this time. And then you do it one more time, like that, and that's a completed splice where the hose has been cut, and you put it back together. Again, please do not repair these hoses with any kind of tape deal. We're to use a splice connector and ferrules to put them back together. And of course, I would have to do the same thing for these acetylene hoses to put them back together. Never interchange hoses. Don't use an oxygen hose for an acetylene, anything like that. Leaks are a hazard and they're a waste of money. So you want to be sure that you examine them for leaks. Take care of them, as you're using them. You can certainly take like a, if there's pressure in the hose. I'm going to demonstrate a leak or a drop test. I'll do a demonstration on that for the group, so you can see how you test a pressurized system. But you can certainly take like a soap solution and just go and you can spray should you suspect any kind of leak.